Thank you. Good morning, everyone. Welcome to Proof of Stake. My talk is about private proof of stake. It's joint work with Chaya Ganesh, who is also here in the audience, and Claudio Orlandi from Aarhus University. So if we talk about proof of stake, we should first talk about permissionless consensus. So if it's about blockchains, that's the question of how can you actually extend this chain. And this is often done using a lottery. The idea is we kind of have this lottery which gives the winner the right to actually make a new block. Now if you say, well, wait, lottery, what I mean by lottery is the following. You all know those lotteries. One of them is called proof of work. Another one of this type is called proof of stake. Now if we compare them, many of you will know, right? The idea is simple. Your winning probability of the lottery for proof of work is just the amount of work you invest. And in proof of stake, it's just the amount of money you actually have you invest into this lottery. This, of course, has some impact on the energy cost. So if you need to invest work to win the lottery, then obviously that will result in a high energy consumption, so not so green. On the other hand, we have proof of stake, where essentially all the energy cost is like, I need to check, oh, I won the lottery, and someone else who sees the block needs to verify that I actually won. And there's also this aspect of who controls the system. If you look at proof of work, then it's the miners, so people who have specialized hardware who actually maintain the system and therefore control it. In terms of proof of stake, it's simpler, right? Whoever has a lot of money in the system actually is also kind of maintaining this system. So if we look at this comparison, we would say, well, obviously, we want to choose proof of stake. But there's the question, what about privacy? AKA, I want to hide my money. So what I mean here is, as a user, of course, you can hide your money, no problem. We saw that in the previous days. There's solutions like Zcash, Mimblewimble, or QuizQuiz, which allow you to have anonymous transactions, hidden accounts, and so on. What I want to talk about today is privacy for the ones who maintain the system, so the ones who make new blocks. By doing so, they earn money, right? In proof of work, that's the block reward. So let's see how this looks for proof of work. So in proof of work, we have the work lottery, and here Alice, she wants to participate, so what she can do is she provides a block template. The block template has some data, right, transactions, and of course, important for Alice because she wants to make money, her reward address. She then invests some work, and if she's lucky, she wins. She gets a certificate from the lottery back, which says, you won, and can attach that to the block, and then Alice publishes this block. But here comes the bad guy. Obviously, the adversary wants to find out how much money Alice has, and it's quite easy for him to find this out because he just simply looks at the reward address and says, oh yeah, that's a block by Alice, so now Alice has block reward more money. So Alice is not happy about that, but for private proof of work, there's not much to be done. In fact, we just use always a fresh address. Each time you make a new block, instead of pointing to your old account with all your money, you just make a new account. And so in this setting of proof of work, the adversary now has no idea by looking at the block how much money Alice is actually making. Because note that the proof here, this certificate, is now based on the block. It's not dependent on Alice. It's just dependent on the block template, which is specified here on the left. So under those two assumptions here, we have privacy. Namely, you need anonymous transactions because now you have this fresh address, and Alice somehow wants to get back her money, so she needs to be able to transfer the money in some hidden way. And of course, we need anonymous way to publish blocks, because if the adversary can see, well, Alice announced the block, then again, he would learn that Alice got a block reward. So for private proof of work, this is pretty simple. We have privacy. So what about proof of stake? So in proof of stake, we start with a stake distribution, so a list saying that person has that amount of money. This is then put into the lottery we have, and now Alice, again, she participates. This time, no investment of work, she just checks, and if she wins, she gets a certificate, which you can use to create another block. Now, privacy concerns. We don't even have to look at the block as a bad guy. We can just look at the stake distribution, and we find out how much money Alice has. So she's not happy. Well, luckily, there's cryptography, so what we can do is we can just simply use committed stake. We hide the stake in this list. So now you just have a list of public keys with some commitment next to it, and that's the accounts. You can also use such systems in anonymous cryptocurrencies. That's nothing new. The problem now is your lottery, right? Your lottery actually has two components. One is I need to check I won, and then someone else who sees my block needs to be able to check that I indeed won the lottery. And this verification now with this list becomes more difficult. But, well, this is cryptography, so we upgrade the lottery. We just use zero-knowledge magic, and somehow the lottery will again work. Question is, if we do that, so the lottery just now works with this list, are we happy about that? The answer is no, not really, because the adversary just looks at the block. So if you look at the block, the proof itself is still identifying Alice. And so now, as this is a proof of stake lottery, so your winning probability is tied directly to your stake, the frequency will actually just reveal how much stake you have. So this is particularly concerning if you have a lot of stake, because then you will publish a lot of blocks, and so we know how much stake you have. So Alice is not happy about this. How can we do better? Well, what we actually want is an even better lottery, where Alice just get some sort of anonymous proof, which essentially says someone won and they published that block. So now if the adversary looks at the block, nothing happens. And again, we have similar to proof of work, we get the guarantees that privacy exists, assuming anonymous transactions and some way to publish blocks unseen. But of course, the question is, such a fancy lottery, can we achieve that? So our results to that is, yes, you can do. So it's feasible for a wide variety of lotteries, not just a lottery where you are allowed to publish a block. You can also use such an idea to create a lottery where, say, you are elected to a committee based on your stake. Now, this is a more theoretical result, as we just show you can do it. But also to show kind of that it's a bit more practical, we actually implemented such a made a protocol, designed a protocol for a specific thing, namely Ouroboros-Prowse, which is a proof-of-stake protocol. What I want to mention here is that there is concurrent work also on this topic by the people actually from the Ouroboros family. This is Kerber et al. They also make private proof-of-stake, but they do not care about the anonymous block publication. So they're perfectly happy if their lottery actually announces the winner. And this, of course, comes exactly at the cost of this leakage over frequency analysis. So if you want to see this more in a picture, this is the difference between our work. What we want to do is this really fancy magic lottery, and they just do this a bit lighter version here. For the rest of the talk, I want to focus here on this result for Ouroboros-Prowse to give you kind of an insight on how you can actually upgrade privacy. Of course, for that, we need to first see how Ouroboros-Prowse works. The idea is pretty simple in this protocol. What we want to have is a leader election lottery. So Ouroboros-Prowse actually splits the time into slots. And for each slot, we have potentially a block winner, and that winner can actually publish a block. The tool they use is called a verifiable random function. For those of you who know PRFs, it's just a PRF with a publicly verifiable proof. So why is this useful? Well, here's a kind of a diagram of how this VRF looks like. You have a key generation, which gives you a key pair, secret key, and public key. You can use the secret key to evaluate the VRF on any given input, and it gives you the output, and that's the fancy part, plus a proof. So this part here, the evaluation function, is used by the one with stake to actually check if they won the lottery. This is kind of the source of randomness in the lottery. And of course, now if they then win, they publish a block, we need to check that they won. So we have, of course, verify function, which takes your public key, the input, the output, the proof, and gives you yes or no. So the Ouroboros lottery looks as follows. We have accounts. So Alice has an account, and it's a well-known account. The account consists of the VRF public key, some signature public key, and of course the open stake, just plain number there. The lottery condition. So when has Alice won the lottery? Well, that's this equation. We essentially sample some randomness using the VRF and check that this is strictly smaller than a function of your stake times a scaling factor, which just makes sure that kind of it's in the same domain. Now, this function phi of stake, if you think about it, it scales. The more stake you have, the bigger this phi. So if you have, for instance, 0 stake, this phi will be 0. So you have not a chance to win the lottery. Then the thingy you get back from the lottery, the one part you actually put in your block, is as essentially saying, well, Alice has won the lottery using that stake. And a bit more formal, if you like, such a proof can look like this. You have a public key which identifies the account which has won the lottery. You have the output of the VRF plus the proof. And you have a block signature. This signature is essentially used to prevent other people from using my proof to actually create another block, right? Because if we don't have this signature, someone else could just take my proof and make a block where they get the reward. Now, if you look at this lottery here, this red stuff leaks information about your stake. So in particular, it's obvious that if you have open accounts, you can just read the stake. But also, like in this proof itself, if you publish this eval VRF there, this gives you already a bound on your stake. So the question now is, how can we do better? So that's kind of given by Ouroboros powers. How do we make that private? The first thing is we commit stake. So instead of pointing at the single account, we point at the list of accounts where each account has committed stake. And then we replace this proof from Ouroboros powers by a more generic proof, which just essentially states someone won. So what does this mean? A bit more formally, the proof has the following form. It says, I know a VRF key pair, a signature key pair. I know stake plus a corresponding commitment and a signature such that the following holds. First of all, this commitment is actually a commitment to my stake. Then there is actually an account in the list which has this commitment in it. So in other words, these two lines say, I own that much stake. Next line says, I won the lottery. Okay, it's just this lottery condition here. And finally, this signature I know here is a signature of the data block under the public key of the signature scheme in my account. This last line again is to prevent others from just stealing my proof and making their own block. Now the interesting question is, how can we do this? So the goal is now to create this proof in zero knowledge. So we need to prove the statement. How do you do that? Well, for those two parts here, you can just use generic Sigma protocols. One note here is that if you want to do that, the commitment should be algebraic. This one here, so the proof that you have an account in the list, you can do that by representing the list as a Merkle tree and then do a path proof. But the interesting part actually happens here in this proof of I won the lottery. So let's have a closer look at that. Our goal is to prove this statement in zero knowledge. That's the same as just splitting it up into saying my VRF evaluated into y, and y is smaller than this function of my stake. Now we know that this is theoretically feasible, so we could say we're done. But actually we want to also show that this is somewhat practical. So let's have a look at this phi. How does phi look like? That's this function. So f is the difficulty parameter. And the function of the stake is just essentially your relative stake. In other words, if you have all the stake, then this function gives you f. If you have no stake, it gives you 0. So it's just kind of this probability. But unfortunately, if you look at this function, that makes it really annoying to compute in zero knowledge, right? You have this exponent up there, and so on. So we want to avoid that, right? If you want to do practical stuff, don't try to compute that in zero knowledge. So how can we avoid computing it? Well, luckily the function has a nice property. It's called the independent aggregation property, and it's this formula up there, which looks complicated. But in more intuitive words, it just says it doesn't matter if you split your stake into 2 accounts or more, your probability of winning the lottery overall stays the same. Okay? No matter if you have 1 account with 100 coins or 100 accounts with 1 coin, your probability of becoming the next slot leader is the same. And we can now use this to actually make virtual accounts in our proof. Instead of proving directly that my stake won, we actually split our stake into virtual accounts for the proof, where each of these virtual accounts has a known size. So this splitting is pretty simple. It's just this binary decomposition of my stake. So each of these accounts now either has a power of 2 stake or 0. And then, of course, we need to show that just one of my virtual accounts has 1. A bit more formally, the statement we want to prove in zero knowledge is the following. Say I know some bits, some VRF outputs y. I know the one account which won, plus, of course, my VRF key and the overall stake, such that A, the bits I just claimed that are bits are actually bits, plus that my stake actually decomposes in the way I just claim. And then the lower line there, right, we say one account won. So for that particular account, we need to make sure that the account really exists, has positive stake. So the bit should be 1. And then the rest is essentially just the VRF evaluation for that specific account. Okay, it's just the same as the top line for one virtual account. Now, how do you prove that? First line, that's standard techniques. The second line here, what we use is a sigma OR proof. So actually what we prove is that this statement is true for one of the accounts, and we do not reveal for which one. The cool part about this is now that here in this inequality, the right-hand side is just a constant. We can pre-compute that. That's the same for everyone. So you don't need to hide this constant in anywhere. And so we avoided to compute phi actually in zero knowledge. There is one smaller detail in here. If you look at the evaluation of the VRF, right, in zero knowledge, if you want to do that, it actually requires the public key. You need to know the public key. The problem with that is we cannot reveal the public key of my account because then you could link it again and you know my stake. In order to solve that, we introduce a so-called anonymous VRF. What they do is essentially they allow you to update your public key to generate a new random version of that public key, which we then can use here to create a zero knowledge proof. If you want to know more about this concept, I refer to the paper. So with that in mind, we have now these virtual accounts which allow us to prove that I won the lottery in a more efficient way. So with that said, we now have the proof. Essentially, we broke it down into these components. For each component, you can use, say, standard tools for zero knowledge to actually prove it. And so the lottery now works as follows. Alice, she can check if she won because she knows the stake. And if the inequality is satisfied for her, she can craft this zero knowledge proof, get kind of this certificate, which is now independent of her, and create here a new block. And so this makes a private version of Ouroboros PROS. So this brings us back here to our results. So what I've shown you today is kind of the idea for private proof of stake in the Ouroboros protocol. But again, I want to mention that it's feasible to do this also for other types of proof of stake. It's not limited to that protocol. The idea of kind of transforming protocols will be similar. It's just like in the details, it will differ, of course, because you have different goals. But it's possible. You can do that. And with that, I'm at the end of my talk. I'm happy to take questions.
If you have a question, please line up in the pathway.
Does this use the DDH VRF?
Sorry, what?
Does this use the DDH VRF?
You mean the VRF for the Ouroboros protocol?
Yeah.
I am not sure in the details. But, I mean, it should work for different VRFs, right?
So the thing is, you have to verify, I didn't see this, you have to verify the VRF proof inside of the Sigma protocol. But then,
I mean, as I said, right, you cannot do it directly using the VRF. You need to upgrade it to this anonymous version of the VRF. It otherwise wouldn't work. Yeah, you would run into trouble. So we actually update this to a different primitive, which has a similar property as a VRF. Essentially, it's VRF, but it allows you to check proof without knowing who actually made that proof. I'm happy to discuss this with you afterwards, if you like.
Have you tried, or what challenges do you foresee in adapting your work for the Algorand protocol?
So in the Algorand protocol, you have the committee-based proof of stake. So the idea, as far as I understood it, is you elect kind of a committee which decides upon the next block. So what you would do there is kind of, you can also locally check if you won, and then your committee messages, you will publish your committee messages with such a proof. So it should be doable. But I have no idea how efficient this then would be.
Any other questions? Okay, if not, let's thank Daniel again.